Okay, it's 3:32. Why don't we get started? Good afternoon, everyone, and welcome to this week's seminar talk. My name is Emmett Antelucci from Center for Imaging Science at RIT, and I'm also the Western New York GRS Geoscience and Remote Sensing Society Chair. Today I have the pleasure to introduce Professor David Long from Brigham Young University, located in Provo, Utah, which is just a little south of Salt Lake City there. He'll discuss that. And he's asked me to abbreviate his bio, so I'll just kind of skim through the quick highlights and then let him introduce himself the rest of the way there. But he's been on the faculty at Brigham Young University in electrical and computer engineering for the last 30 years. He's full professor there where he teaches radar, remote sensing, communication. He's also director for the Center for Remote Sensing and head of the Microwave Earth Remote Sensing Lab, at least since 2012 has been Associate Dean of the Ira A. Fulton College of Engineering and Technology. Received his undergraduate and master's degree in EE from Brigham Young, and then went out to California for a PhD in EE from USC. In the mid-ish 80s up to 1990, was employed at JPL in the radar science and engineering section, was also group lead in the radar systems engineering group and responsible for the design and development of the NASA Scatterometer system. He's been PI for a bunch of programs, NASA related in a variety of areas, published about 118 journals, 300 conference papers, received a bunch of NASA awards, and is associate editor for IEEE Geoscience Remote Sensing Letters. And finally, he's actually co-author of the 2013 textbook, Microwave Radar and Radiometric Remote Sensing. With that, let's welcome Dr. David Long.
Well, I'm grateful to be here. Thank you for inviting me, Emmett. It's been fun. I've been visiting with some of the faculty there at RIT and have been enjoyed myself immensely. I've got kind of a little talk here that I have some slides that talk about these activities. Let me kind of finish the introduction a little bit. You know, he gave you some of the dry background there, okay? But the part that was interesting is I used to work for NASA's Jet Propulsion Laboratory, where I designed radar systems for spacecraft and started my remote sensing career in microwave remote sensing, which this talk's all about. Now, when I worked at NASA, when we have some big review, we put on our coats and ties. We put on what we called a dog and pony show to show all the cool stuff that we were doing. Well, since you guys are all VIPs, I think I should do the same thing. So there's my dog and my ponies. My wife raises miniature horses, and I get to help her out with that process. So when we talk about shoveling the manure, sometimes I'm literally doing that sometime there. So the work I work with is at the Microwave Remote Sensing Lab. We have just a few students. Well, actually, a lot of students, but there's a few of them just sitting around here, talking around, doing various aspects of remote sensing, particularly in synthetic aperture radar, in scatterometry, and in the use of those kind of technologies. So what's remote sensing? Now, you guys are doing this a lot, but let's step back for a second. Really, to get technical, remote sensing is seeing from a distance. And all of you are expert remote sensors because you use your eyes. Your eyes allow you to see the light reflected from some other source, come to you, tells you what's going on at a distance. Now we've got modern technology, cameras, telescopes, and radar to help us see things from a distance. So here's Utah, an optical frequency seen from space. You know, my institution, BYU here, is just immediately to the east of Utah Lake, which drains into the Great Salt Lake. Salt Lake City sits right there. We start out with remote sensing looking far, far away. And as we move in closer, you know, we start to see the world getting more and more detailed until finally it comes down into a human scale view. So all that's based on the electromagnetic spectrum. What can we see? It's kind of a diagram, a map of the electromagnetic spectrum. Typically, of course, and this is new information for most of you, that we see with our human eyes in the visible spectrum. Right here, we see our RGB colors. We also use infrared a lot and ultraviolet for remote sensing. Well, my specialty is in the microwave band. These are much lower than infrared frequencies, and we split that frequency range up into different bands, frequency wavelengths, to do different things. And I like to joke that I want to show you the wavelength of my sensing. Either I can do it with some fingers or maybe with some hands, but if it's longer or shorter than that, it's not microwave remote sensing. Now, what are the advantages of microwave remote sensing? Why did I just use the cameras? Well, the main thing is we see different things at different frequencies depending on the wavelength. My rule of thumb is that the electromagnetic waves interact best with objects that are larger than them. So we can use the microwave remote sensing to sort of differentiate between small objects, molecules, for example, and larger objects that gives us something about the texture, the macro scale texture, the sort of human scale activities that are going on there. But radars and microwave remote sensing can operate at night. They're minimally affected by dust, by rain. They provide their own illuminations, which gives us some control, like a flash camera. We can do kinds of things we couldn't do otherwise. We can typically penetrate the surface much deeper than an optical sensor, particularly in vegetation or dry soil. We're going to talk about that today. And you can study the scattering mechanism. We'll find that's a very useful feature to see these different features. We also have something unusual is that we can do active and passive remote sensing from space. Active sensing from an optical frequency is very difficult from space. So if I take the general field of microwave remote sensing, I can split it into two major areas. Radar, which has an active transmitter and a receiver, and radiometry, which is basically only a receiver. Okay? Within those two separate classes, there are a number of well-known instrument names. On the passive radiometer side, we can build a classic radiometer. Sometimes we call them sounders when we use a different geometry for those. And we also have synthetic aperture radar or radiometers that we can use. The active side is a little more fun. I like that side. I like to stay active, and so we get to do that. We have non-imaging radar systems like scatterometers, altimeters, airborne radars, the weather radar, the thing you see at night, and synthetic aperture radars like imaging radars. They're essentially radar cameras. They come in several flavors too. The two that I'm going to talk about are just imaging, synthetic aperture radar, or SAR. And we'll talk about interferometric SAR as well. The key idea in an active system, in a radar transmitter, is that we transmit the signal and measure its reflection. Because we control the illumination, we can modulate the signal and we get coherent returns that we can do some extra processing to improve our resolution or collect additional information about our target. The advantages of radar remote sensing is that we can often extract scattering information, the mechanism about our target, which gives us really powerful information about it. Nothing comes for free, so there is some disadvantage, and the biggest disadvantage is we have to carry power, the extra power, because we have to have a transmitter. That needs extra mass if we're in a spacecraft or an aircraft, and we got to supply it to that. We also run into a problem which is unique in microwave radar, and that is coherent signal effects. We see this with laser when we get speckle. We point our laser pointer to screen. We see the speckle around the outside. We get this effect with radar as well, and that can cause issues. But we can also exploit the coherency to see things we couldn't otherwise see. Now, radars fundamentally measure three different properties. They measure time delay. That's the time of flight from the radar to the signal. That tells us something about the flight distance, what we call the range or the slant range. We can measure the relative velocity of the target by looking at the Doppler shift. When the target or the radar are moving relative to each other, then we can see that velocity, and that allows us to do some interesting things. Finally, the radar, of course, measures the reflected power. Sometimes we call that the radar cross-section. And those are the three fundamental measurements. I might add a fourth, and that is the geometry. We have an antenna, a lens, in effect, that directs the microwave signal in one direction. And so that gives us a geometric discrimination to look in one direction or the other. Now, because in a microwave sensor, we can do some good things. We can measure polarization. Now, we sometimes do this optically, but because with a radar, we control our polarization very carefully, we can exploit the polarization dependence of our target to gain more information about it. And then we can also choose a wide range of frequencies. And this is critical because the microwave band extends from a few millimeters up to essentially a meter. Like that gives me a huge range of target sizes that I can optimize my signal to be resonant with. Okay, let's go on and talk a little bit more about this in practice. Radar remote sensing is all based on the radar equation, which relates the received power to the power that I transmit. The rest of the parameters in this are things that have to do with the radar, my antenna gain, the wavelength, which is related to my frequency, the distance I am from the target, the area of my resolution element on the side, which would be a cell or my footprint. We'll talk about that. And also the radar cross-section of the surface. Now, this is the thing we're generally interested in because that is going to be a function of the geometric properties and the dielectric properties of the surface that we're going to look at. We'll talk about that in a lot. Now, we also get noise, and that noise comes from the classic equation, from Planck's equation for KTB, where the amount of power we measure is a function of the temperature, the radiometric temperature, and the bandwidth over which we make it, and Boltzmann's constant. For a radiometer, this is what we measure. We measure the noise only. For radar, we're interested in measuring the reflection, which is this. And unfortunately, we get this along with it. So we want to take that out. Okay. Now, when we look at a radar, we transmit a signal from the radar and it bounces off the surface. If the surface is very smooth, it's flat, then we get almost no return. It's very black. That means there's no brightness, no echo return. But when the surface is rough, then we get scattering in all different directions from different features on the surface, and we get some sort of backscatter imaging capability. Now, when we have mixed cases where we have something like a canopy, a forest canopy, some of the radar signal will scatter from the canopy in a volume scattering method. Others will penetrate through the canopy down into the surface, scatter off the trunks and off the surface. This gives us some unique capability. By changing the frequency of my radar, I can penetrate deeper into the canopy and measure at different depths all the way down to the surface. In particularly dry soil conditions, deserts, the signal can often penetrate the surface of the ground and actually bounce off what's below the surface. And I'll show you some examples of that toward the end of the talk. Finally, in urban areas where we have a lot of right angles, we can get what we call corner reflector effects, which bounce the signal back to us in a very strong way. And so we typically see very bright targets, roads, buildings, curbs, things like that, cars. Going back to the surface roughness a little bit, the scale of the roughness plays an important role. When the surface is perfectly flat, most of the signal bounces off. When it's a little rough, we get scattering in, kind of a broad pattern, kind of like an antenna itself. When it's very rough, the scattering pattern gets very rough. Some kinds of surfaces are somewhat periodic, like waves over the ocean, in which case we decompose it into a sort of set of flat facets, so we can use this kind of scattering. And then the rough surface, which rides on top of that, and look at the surface scattering that way. Again, this allows us to extract and model geometric properties of the surface from the microwave signal. Now, we're going to mainly be interested in what we call backscatter, where I transmit and receive from the same location, but we also have bistatic scattering when I transmit from one location and receive from the other. That's a little more complicated problem. It's an ongoing area of active research, but backscatter is the key case. And when you look at the backscatter, we call the backscatter the normalized radar cross-section, which is the amount of backscatter divided by the area, okay? A very smooth surface, if I plot the backscatter versus the incidence angle is defined to be when I look straight down at 0. When I look off at the horizon, that's 90 degrees. So looking straight down, I get a mirror reflection from a smooth surface. Very rough surfaces give me pretty flat surfaces, very flat. And so if I look at various surfaces and the backscatter versus incidence angle, I can discriminate between what's a rough surface and a smooth surface by this roll-off characteristic. This gives me an opportunity to discriminate whether the surface is, say, a surface of water, maybe water covered with vegetation, okay? And I'll show you some examples of that too. The other kind of scattering we get is volume scattering, where I have a layer of scatters. They might be leaves, might be sand grains, it might be snow crystals. The signal comes down and bounces off the crystals. A lot of it goes in all different directions, but some of it penetrates all the way through the ground. We'll get multiple bounce scattering off of this. And what is normally a very small scattering object can still produce a very bright, very rough looking surface because there's so many of them. And I'll show you some really great examples when we look at snow scattering. So here are some radar images of the Earth at 14 gigahertz. This is the frequency of that new SAR you're going to get, okay? I've actually masked the ocean off because I want to talk about the ocean. You're just looking at land surfaces, okay? So you're looking at the normalized radar cross-section on a pixel grid on the Earth's surface wrapped on a sphere. You can notice that ice is very, very bright. Dark areas up here correspond to deserts, the Taklamakan Desert, the Sahara Desert up in here. That's because the signal is reflected well by ice and vegetation, say in the rainforest of the Congo or of the Amazon, and not so well from drier areas. So we immediately see, we can see some terrain information by just looking at the raw, quickest look at this. The final kind of scattering is something known as Bragg scattering, sometimes known as resonant scattering, where the surface, like the ocean surface, or perhaps plowed fields, or perhaps sastrugi, which are snow dunes, sand dunes as well, are periodic. And now when we look at scattering, if I look down the troughs, it's just the surface. But if I look across, I will see resonant when I'm at the right incidence angle. I'll get a very strong scattering because the change in wavelength from peak to peak is a multiple of the wavelength. And so it gives me an enhanced backscatter. We can exploit this to actually measure wind speed over the ocean. How in the heck do we do that? Well, wind, air, moving over the surface of the ocean, drags the surface along a little bit, producing waves. Now, the actual waves that are produced by wind blowing are really quite small. They're capillary waves or perhaps capillary gravity waves, which are very small. But water waves, as they interact in a nonlinear way. This is different than electromagnetics, where two waves can pass through each other without modifying each other. Two water waves will modify each other because the dispersion ratio is different in water as a function of frequency. And so small waves become large waves. And large waves become bigger waves until we get into swell, which is meter scale waves, which is kind of what we think of as humans. We think of waves. But this resonant scattering occurs with wavelengths of the order of 1 inch to a few inches in length. Okay? It turns out that those small waves are in equilibrium with the wind. That is, the wind blows, it quickly creates a surface of the wave covered with those size waves. Most of you have been at the water and a lot like a dock or quay, you watch gusts of wind blow over, and you see how the surface gets roughened. That roughening is called cat's paws. And those are these capillary gravity waves that produce these waves. Well, if you measure the backscatter, the normalized radar cross-section, versus the azimuth angle of the wind, remember you're looking down the direction or across, we see a change in the backscatter with direction and with wind speed. That enables us to infer from space the wind speed and the wind direction over the ocean. So we've built radar sensors like the one shown up here, which is the QuickScat scatterometer that flew from 1999 through 2015 when we 2017, I guess, when we finally had to turn it off. Still operating at that point. It makes observations by measuring the backscatter from different directions, which allows it to solve for the wind speed and direction of these curves. You know, it's not a one-to-one function, so it's a little bit complicated, but we can get the directions out of that. Now, that was called a rotating beam scatterometer, a conically scanning pencil beam. It actually has two antenna beams that scan out a surface. We can use signal processing to split the footprint up into slices. So they're colloquially called eggs and slices. These slices provide finer spatial resolution than you'd get with just the footprint. We also have fan beam scatterometers. The very first scatterometer, CSAT, which flew in 1978, was a fan beam. The Europeans are flying some fan beam scatterometers like they have this beam pattern on the surface. And as they pass over a point, they first observe from a forward-looking beam, then a side-looking beam, then a back-looking beam. Those multiple directions allow them to infer both wind speed and direction simultaneously. So a whole series of scatterometers have flown over this. I happen to have been blessed in my career to have worked on virtually all of these except for CSAT, which was flown when I was in college and I wasn't really aware of it. but I was key designer for NSCAT and the Sea Winds, and then these other two are sort of copies of our design from the Sea Wind system. And then we contributed to some of the other parts of this and processing the data for ASCAT and some of the other design. These sensors, the scatterometers, were primarily designed to measure wind over the ocean from space. So what applications would that have? So here's a picture of the QuickScat satellite. This little dish across here is about 2 feet in diameter. It spins at about 18 RPM, which is about as fast as I can turn my hand, in my little video up there in the corner, okay? So this spacecraft is actually pretty small. It's big enough to small enough to fit in my office. It's very unusual for a remote sensing system up in there. This is a sequence of an animation of photographs of wind blowing over the ocean, and of a hurricane passing during one day over the coast of the South Carolinas. And we can see all the cloud tops. These cloud tops are great for tracking the big features, but it doesn't tell us what's going on at the surface. To do that, we need the scatterometer. So here is a coincident pass of the scatterometer over the same area during just toward the end of that day right there. The colors here tell us the wind speed, and then the directions are those little arrows. And you can see that we have wind vectors about every 25 kilometers. The weather forecast, their weather forecast, their jaw falls on the floor and rolls around because they don't even know what to do with this much data. They're used to a few buoys, a few ships here and there, and they try and interpolate between them. But now they have this data. So while QuickScat was operating, the forecasting skill went up. They were able to forecast days longer than they were in the past. As I finished my work at JPL and came to BYU, I started thinking about the problems with the fact that we can't get closer to the shoreline because the land kind of contaminates the wind measurements. And also this resolution is pretty coarse. Can we do something better? So we developed techniques to improve the effective resolution of the scatterometer data. So here's the zoom in on what we produce now. Those arrows are are now shown by wind barbs up in here, and the background shows you the color at a much finer resolution. Instead of 25 kilometers, this is 2.5 kilometer resolution. And we see that we caught the eye of the storm right as the eyeball was coming onto the outer banks out here on there. And we can see how we have really incredibly high winds up in here and a very calm center of the eye. And we can see a lot of details related to the structure of the storm that affect its propagation direction and how destructive it's going to be. So really, this was designed to be a global wind sensor. So here's that picture I showed you before, where now the backscatter is shown over land, but the wind speed field, and then these streamlines show the wind direction, show the wind direction over that. This is what scatterometers were designed to do, measure wind. But we could take the measurements we get over land to do other things. And just this one picture shows us some really interesting features. Notice the bright dots that occur here in the United States, and if you look over here in Europe, those are actually cities. They appear brighter because of this corner reflector effect of all the buildings that are in there. So we have examples of tracking hurricanes as we watch them develop just off the coast of the Cape Verde Islands. Typically the storm conditions that lead to hurricanes that propagate across the Atlantic. That's what this system does. My lab put together one of the largest databases of hurricanes taken during this mission at high resolution that the forecasters have been using at the National Hurricane Center. Of course, they have to do real-time forecasting, which helps. But here are an example of Hurricane Katrina. Here's our image product on the same color scale as the conventional 25 kilometer products that the NASA originally produced and what the hurricane forecasters used to use. And we can see a lot more details about the eye wall and some of the structures that occur in there. Just for fun, I thought I would show you the tracks of all the hurricanes that hit the east coast of the United States during the QuickScat mission, just not, they were in the South Atlantic, I should say, in the United States. But this is a publicly available database, fun for doing it. We used to do this in real time more than we do now, but with the sensor down, we can't do quite as much. Skipping this picture. Now, to illustrate how this could be used, this is a picture of the Hawaiian Islands. This is the Big Island. And then Oahu's out here. This is Maui sitting right there. This is during a big storm. The wind is blowing from right to left, and the islands poke up high enough that they're above the boundary layer, which is the area, the lowest layer of the atmosphere right next to the ocean that is primarily affected by the ocean only. And when you're tall enough, the winds have to go around the island. And so the winds get accelerated between the islands, and you get very low wind speeds in the lee of the island. This is very difficult to observe with the low resolution winds, but very easy to see with the high resolution products that we produce. And so when we were looking at one of these, we saw something like this. Now, this is the more conventional situation. It's not storm. The wind is still blowing the same direction, but now it's blowing the standard speeds around the islands of Hawaii, 15 meters per second. That's very typical out there. We still see a lower wind speed in the lee. We can see some interesting patterns out here. These are caused by kind of the weather disturbances out there. And then we see these very sharp wind speed peaks. And those used to be flagged as errors in the low resolution scatterometer data because they seem to be anomalously high. But we realize these are caused by thunderstorms. We get a lot of backscatter from the raindrops and from the raindrop disturbed surface. And so when we try and retrieve the wind there, it's contaminated by this. And so the retrieval is an error. And so my lab then developed some techniques to measure the rain and the wind simultaneously. And I'm going to talk about that and some of the other applications here. We had the unfortunate experiment where when there was a big oil spill in the Gulf of Mexico in the mid 2010s, we were able to collect our radar data. So this is a C-band, that's 5.4 gigahertz, image taken by the ASCAT scatterometer, passing right over the end of the Gulf of Mexico, or end of the Mississippi Delta out here. And this is the Deep Horizons oil spill. It's large enough to actually show up on these fairly low resolution images. These are only 2.5 kilometer pixels. So they're pretty big. It's a very coarse scale image. And yet the oil spill is big enough to see on there. The reason it shows up is because this is the wind roughened surface. So now we're showing backscatter, not wind. The oil dampens the wave spectrum so that we don't produce these small waves. And so we get no backscatter back. Now a smooth surface bounces right off. And so it shows up as a dark hole, the data. Here's an animated series of images that shows up how the Great Lakes freeze up in the winter. You're looking at basically 1 KU band image per day. This little cloudy stuff you see in there is the formation of lake ice, which is then moved around by the wind up in there. So we see that the Lake Superior, or I guess that's Michigan, excuse me, Superior down here, kind of basically completely froze over. And, some of the other lakes up there, I guess you guys are not too far from right here. Now, the noise that you see, the speckly noise, is caused for 2 reasons. Number one, the measurements are quite noisy, and so you tend to get noise, but also you're seeing variations in the temperature of the surfaces. The actual land surface is covered with refreezes and thaws, covered with snow. So you can actually kind of watch waves of weather pass through as the weather conditions change through this sequence up in here. So this became a regular product provided by the National Oceanic Atmospheric Administration, the Weather Service, to mariners in the Great Lakes using our data. We actually wrote all the software, did all the analysis that did this thing for them. The most interesting story we have is a lost iceberg in Antarctica. This is the very first backscatter image that me and one of my students put together at the very start of the QuickScat mission in 1999. One of my colleagues, John will know him, Lenny Jones, was there with us. We were calibrating this new radar QuickScat that we just launched, and we created this image, and I showed this on the screen, and I said, wow, look at this beautiful picture of Antarctica. So this is Antarctica covered with glacial ice. This is the sea ice mantle around the outside. Here's the southern tip of South America. And I pointed out that I could see this giant dot out there. It was an iceberg. And one of Lenny Jones' PhD students said, well, shouldn't you tell somebody about that? And I said, oh, the National Ice Center, they just track these things. They know about this thing. A couple of days later, we're going to do a press release. NASA likes to do press releases. And so they wanted to use this image. And so I called the National Ice Center and said, hey, what's the name of that iceberg that's sitting out there? And there was a whole flurry of activity, like 5 minutes. And they said, you found our missing iceberg. That iceberg is B10A. It broke off the continent down here, actually down here, had been sitting grounded for several decades and had, in the last 4 months, floated around here right into a shipping lane in the Drake Passage. And so we discovered a secondary use of this sensor was actually to detect icebergs. So we started providing iceberg tracking information to the National Ice Center and also to the International Space Station, where the astronauts love to take pictures of icebergs. So we kind of tell them where it is, where to point their camera, and take pictures of the iceberg. So this is one they took. This is a typical Antarctic tabular iceberg. They are very, very large. They're formed when a glacier that's flowing out over out from the continent out into the ocean, the end of it breaks off. This thing floats away. They'll be 300 meters thick, and here's 25 by 12 miles in size. Okay. This is a picture of that iceberg taken from a ship. We used our real-time tracking capability to help direct ships to study the icebergs. The icebergs carry dust in the ice, and as the iceberg melts, that dust is released into the ocean, fertilizing it. So you get huge biological blooms in the pelagic ocean here that actually do things. And so since this iceberg is so big, 9/10 of it are below the surface, if it's 60 feet high, which they measured, that means it's 600 feet deep. So this happened to be kind of a shallow one. It's been melting for a while here, but you can see what that looked like. I'd say it was cool, but that's a little redundant. So we uh, we ended up tracking a lot of these icebergs over time. So this overhead picture on the left is the only satellite image, besides the one we collected, of B10A. It's 65 nautical miles long by about 25 nautical miles wide. The little dandruff you see down there are 1 kilometer sized icebergs. Okay, that iceberg, you can see it in this little animation I've got here. There it is right there where we found it. We started taking one picture a day. There's another iceberg that we knew about. You can see several others moving around there. And you can see these icebergs moving around. Remember, these things are 50 to 60 miles long. You look at a couple of mating paramecium out there in the water. They come out here to South Georgia Island of Shackleton fame, and you can track these icebergs. We're actually watching one that broke off the Larsen ice shelf, that was the Larsen ice shelf, that's now moving right up there to follow the track of A22B, right to what we've now learned to call Iceberg Alley. Look, what about the other features in this image? This little weird ghosty stuff, this is actually the radar backscatter from the ocean surface. It's moving around because storms move very quickly. Okay, and you're seeing the roughening of the surface. Where it's very bright, the wind is blowing hard. Where it's dark, it's more calmer. You can see wind shadows around the island of South Georgia. The wind and the currents are mostly blowing that direction. You can see the movement of the sea ice. Here it's melting back in the summer. You see the formation of polynyas. The sea ice melts away. Then the movie will restart, and the ice starts to regrow up in here. And you can see how the wind, katabatic winds from Antarctica, push the ice away. This is multi-year ice here. You can see the movement of icebergs tracking the Shackleton. Started out over here and worked his way across here, really part of the 19th century. A lot of really cool data. Okay, so as a result of this, BYU became one of the primary iceberg tracking places in the world, at least for Antarctic icebergs. And so we've created this enormous database of iceberg positions that we extracted from the whole scatterometers. I showed you the pictures up in there, and we continue to keep track of that today. This ice conditions in the Weddell Sea are really important because this is an important area for Antarctic water formation and bottom water formation, because this is where cold water sinks to the bottom of the ocean, flows along the bottom, comes up to the equator to be warmed, and this salt water, warm water cycle, Helios cycle, is really critical in maintaining Earth's climate. Well, this allowed us to answer an interesting question. Somebody had pointed out, by looking at the icebergs that the National Ice Center tracks, their track of this blue line up here. And in 1999, people were commenting, hey, this line is starting to rise up. Maybe this is evidence of global warming. So then we went through and tracked all the data from all the sensors that were available. The first radar observations are right here. This is in 1978 from CSAT. Then we have the NSCAT scatterometer, the red data up through here. I'm sorry, this is ERS1 scatterometer, this is NSCAT through here, and then this is the CWINS, the QuickScat scatterometer up through here. And we do in fact confirm that there is an increase up here, but over here, the technology that the National Ice Center was using was inadequate for tracking icebergs. They were using ships. They didn't start using satellites to right here. So the initial undercount was due to lack of technology. And then the counts seemed to be very accurate until we had two major calving events. Every few years, like 50 to 60, there were major calving events where the end of the Ronne and Ross ice shelves break off and float away. And this creates a large number of icebergs. The last time that happened was about 50 years before this. So these two events are well within the cycle of climate variability. So there's no evidence from this iceberg count. Now, as we've continued the data into the present, some more recent iceberg breakouts are something that had never happened before. We've had the collapse of the Larsen ice shelf, which has created some very large icebergs that have never existed before. That ice shelf has existed in the form that it was in for at least 10,000 years. And now most of it is actually gone. And with that being gone, it acts like a dam for the glaciers behind it. So more ice is flowing out into the ocean, which will sort of drain part of at least the glaciers in Antarctica and raise sea level in the process. So here is sort of an animation showing the movement of sea ice around the continent of Antarctica. We've taken the wind off in this case because we were just interested in the movement of the ice. Okay, and you can see the movement of some icebergs out in here and some that are up in there. You don't see the formation of some of these lobes, which are being driven by storms in the South Pacific. This interesting situation up here is due to the refreezing of polynyas that occur, and the ice color, the brightness here, tells us something about how thick it is and how long it formed. Now, as we look at this, we can see a couple of interesting features. These are the ends of some of these glaciers that come out. This is the Ross ice shelf and the Ronne ice shelf up in there, the glaciers that for that where these icebergs come from. So if I zoom in on those, we actually have images collected at Ku band, 14 gigahertz, and at C band. The hole in the middle is due to no coverage gaps there, but we see some very differences in the different frequencies. The shorter frequencies of Ku band at 14 gigahertz scatter for smaller features. These are the Antarctic megadunes, huge 100-kilometer long snow dunes. They're only a few meters high, wavelength of a few hundred meters, the areas where they form. They form here, and then the winds, it's really cold there, blow down the surface. Because of the rotation of the Earth, they get curved. They drain out here through the Avery Arch Shelf or out through Queen Maud Land or down here through some of these other areas up in here. And these all alter the conditions up here. The C band is a larger wavelength, is more sensitive to it. You may have heard about West Antarctica. Well, West and East Antarctica don't make a lot of sense. But if we look at a map, we call this West Antarctica and this is East Antarctica. West Antarctica is drained by these two ice sheets and is known to be unstable. Should the climate warm enough, the ice that's here will quickly drain away and would have a significant impact on that. They've already observed thinning of the ice shelf up here by sending drones underneath the Ross ice shelf up here. I combine those two images into one image to help us illustrate the features we can see. Here's the color scheme showing different polarizations of the radar backscatter. And you can see the icebergs, they show up really well. Why? Because we get a lot of scattering, volume scattering from that snow and ice at both C band and Ku band, where the ice is melted and then the surface is refrozen. Where the surface is never melted, you get this beautiful golden color, where the arrangement of the V and H pole is different because this is smaller grains, and you don't get as much scattering from the larger larger wavelengths there. And you can see the edge of the ice sheet, the melted sea ice. It's very irregular here, and some information about the wind. We've also used the scatterometer data to study deforestation in the Amazon. So this particular image shows a Ku band backscatter image of northern South America. This is the Amazon River, the delta up here. Whoops, clicked on it. Sorry about that. This bright area, you get a lot of volume backscatter from the Amazon rainforest. This is the jungle, Tarzan of the Apes kind of thing. And so you get a very bright return up in here. This is savanna and grasslands down here. And we compared images taken in 1978 and 1996. And where we saw a significant change, when it was 3 sigma change, we did it with pink, and 2 sigma, it's yellow. We can ignore what happens in the mountains. But along the edge of the Amazon rainforest and along the coastal rainforest, we see dramatic changes. Here, the Brazilian government put in a dam on the river, the Manaus River up here, and so we see a lake that formed. They put highways along here and up in here, and you can see how people have gone into the Amazon, cut down the rainforest, and done it. We can see the city of Sao Paulo, Brazil, down here. So it's very sensitive to vegetation type. In fact, we use that to do some classification. I'll show in a moment. Now, what I've been showing you so far is the scatterometer data at a moderate incidence angle, about 40 degrees. If I look at basically straight down, I see this KU band image. Now, at this lower incidence angle, all the scattering I'm looking at is specular scattering, kind of what's off the ground. I am getting some scattering for the vegetation that makes this kind of cloudy, but I'm really sensitive to any liquid water. So here's a floodplain. This has a name which I've forgotten. This is the altiplano salt flats that occur up in Chile, which is one of the brightest radar reflectors on the planet up in here. You can see other floodplains that occur out there, seasonal floodplains. See the city, and you begin to see outlying cities and the settlements up in there. This has a little bit finer resolution than the scatterometer data, but by combining these two, we can do some cool stuff. So in the interest of that, I want to kind of show that here. I've done the same thing with low incidence angle KU band data and high incidence angle data. The swamps show up really well along the edge of the Sahara Desert. The Sahel is the shoreline between the deserts up here. And notice how nicely the deserts show up in the scatterometer data. Here it's so vegetated, we don't get as much information. But by combining these two, we really get nice views of what's happening in that. Okay, so let me go back a little bit and talk about this classification. So here's the radar images. And so we performed some classic classification experiments where we just took the data and we did some ground truth that we got from UNESCO, and then we colored each vegetation class by its color and found out how nicely they correspond to the backscatter value. Okay, so this looks like I just colorized these, but in fact, this is vegetation classes. And so we classified forest, woods, and shrublands, and here's a classic classification accuracy. We're pretty accurate in getting forest from the other things, a little less so in the grass shrublands, but it's still not bad. But what's more interesting is when we do a slice through the data, we see some of the details here, okay? And we can actually block the forest into different classifications just based on the backscatter value. And then when we do a classification, oops, I left the plate out, sorry. I had a table of classifications of how accurate all these sub types are. And it's really quite interesting. It's interesting to know that if you track each vegetation class as a function of time, you can watch during the summer, the vegetation kind of droops, and so the scattering changes. And as it gets wet or it rains, the vegetation comes up. So you can actually track vegetation vigor by the change in the shape of the vegetation due to the amount of moisture in the vegetation at KU band. So this was kind of an interesting discovery. The scatterometer is pretty low resolution, but the synthetic aperture radar data, especially when used at multiple instance angles, can be used to map vegetation vigor as well. We could have other applications of scatterometer data. Here's some backscatter data showing kind of northern and southern Africa up here. Here's an animated sequence of backscatter values where we kind of look at the peak value that changes. This is an anomaly of the change. We watch as the rainy season moves the central moisture up and down past the Congo, which is the green area up in there. So in the southern winter where they get a lot of rain, it does all the plains of Africa, then it goes up and waters the where most people live up there in the northern part, just below the Sahara Desert. It's when that cycle changes that people get into droughts. This also allows us to identify we have enough flooding to get a lot of mosquito production and therefore to track malaria indirectly by looking for mosquito habitat. Okay, I want to change subject for just a second here and switch back to the Arctic for a second. Talk about Greenland, which is the largest island in the world. It's covered with a mountain of snow. It is more than a mile thick. The snow has gotten so high at the top that it never melts. It's a mountain up there, so it's dry. But the weight of the snow is so heavy that it forces the ice to flow like a glacier off to the sides. And so we can, as you go downslope, the weather gets warm enough that sometimes the surface of the snow will melt. The water will percolate down into the surface where it'll refreeze. That'll form little buried chunks of ice in there. We call them lenses or glands. During the summer, it melts enough that you get the snow actually gets wet, we call it wet snow. And when it's really wet, so it's saturated, squishy stuff, the stuff you hate to go in the winter, that's the saturated snow. And you can actually map these different regimes, these facies in the snow, by looking at the backscatter as it changes as a function of time. The weight of the snow is so heavy, it's actually depressed the island center. So if Greenland melted, it would be actually an archipelago with just islands around the outside. So here is a combined image of Greenland. Okay, this is taken during the summer, during the melt season, just at the beginning. Okay, there's the day, Julian day, and it's just begun to melt around the outside area here. This white area is that wet snow zone, which is melted and then refrozen during the year. It has not melted yet. This is the bare ice and the melted snow zone down here. Okay, the dry snow is up in here, where we never melt. There are two different colors here, which we determine is because there's two different regimes, areas where you get the snow accumulation. You get more snow accumulation on this side of the mountain than on this side, which is very interesting. No one really had recognized that prior to this. If I take a couple of little boxes of points in here and plot the backscatter as a function of time, we see that as a function of time, the values kind of floating around here. I'm doing C band and KU band, okay? Kind of floating around here, pretty constant. And as soon as the snow gets warm enough, it starts to melt. A little liquid water forms, and it dramatically changes the backscatter value. It changes from volume scatter, where I'm getting a lot of scattering for these little tiny crystals, but it goes deep into the snow, to as soon as some water forms, it won't penetrate wet snow. And so it has to reflect off the surface, but there's not very reflective, and so the backscatter drops. Okay, and so we get this huge drop in backscatter, which tells us when it's melting. Now on the dry snow zone, the backscatter remains quite constant. The KU band, shorter wavelength, we get more backscatter from the ice. The C band, longer wavelength, penetrates deeper, but has less backscatter. So there's quite a few dB difference. The scales are different between these two. But this gives us a mechanism to differentiate between melting and map this over a climate. So here is a season from winter to summer, allowing us to look at the change in backscatter. We can see the melting cycle, a couple of data points down there. Interest of time, I'm not going to give you a lot of time there. Here's the punchline though. Here I've taken the average backscatter over 3 decades and subtracted images from each one of these years and shown the anomaly, the difference between them. This is from CSAT, this is all the way from CWIN, and shown the difference. So this is a change in backscatter, which is due to, conditions have changed on the surface. As we look at this, we can see this black area has gotten lighter. Okay, that corresponds to the fact that there's more melting and refreezing going on. So it's very clear that Greenland has gotten warmer and done a lot more refreezing and melting since 1978. This is incontrovertible evidence of that. Okay, when we look right here at this area up in here, these melting zones, how much they've changed, we see how the area's even gotten bigger in more recent days. Paradoxically, when we look at the dry snow zone, looks like PowerPoint has shifted some of my arrows. It's supposed to be right here. Sorry about that. But this area up here is the dry snow zone. We see it's getting darker, which means there's more accumulation to bury anything, the previous ice slab layers below that. Well, that's actually consistent with warming conditions too, because a warmer climate produces more accumulation, or produces more snow. So we have both more snow occurring and a lot more melting. Which one is winning? The scatterometer data can't directly measure that. But recent observations from GRACE, which is a gravity measuring system, confirms that Greenland is losing ice at a very impressive storage rate. Actually, on the high side of the worst case scenarios ever predicted for the amount of melting in Greenland. So here is a time series that shows that melting in Greenland there. It's also showing you the sea ice. I've taken the wind off and I'm just showing you ice. The multi-year ice is this bright area in the middle. It's much brighter because the surface is very rough. It survived the summer and then refrozen. So that's the permanent ice cap. The darker areas out here represent first year ice. It's ice that was created and refrozen in 1 year over one season. And so you can watch as the waves of warm fronts pass over the ice now. Those are the melt, causing it to melt and to refreeze. And then now the winter's starting, and it's all frozen, and the ice starting to grow out. Okay. Well, people are really interested. Is the Antarctic or is the Arctic ice cap actually changing? So what we did is we took a histogram of the brightness temperature of the backscatter values of the sea ice as a function of time. So a slice along here is a histogram of the brightness values, and we did it for each day of the year. And you get this beautiful shape here. There's a peak up here right during the middle of the summer. During the winter, it freezes. You get more sea ice being formed there, and then it's going to remelt. So if I take that histogram, turn it up, kind of make it into an image, this is the summer. It's all melted back. The only thing that's here is this is the backscatter from melted multi-year ice. It then refreezes, becomes very bright, and then that stays through the whole year, okay, in the winter. But we have some production of fresh new ice, new first year ice. So we see a large percentage. So you kind of see the distribution of ice, the total area of ice starts out as totally first year ice, till becomes dominated by, by multi-year ice, dominated by first year ice. You see kind of the pattern I've shown there. Well, I can discriminate by drawing a line between the two, between multi-year ice and first-year ice, just by looking at the backscatter. Very simple discriminant analysis. Probably some of you have done this or will do something like this in your classes. So we developed a technique where we automatically do this. We take these two sets, we do it, and we map them. So I map all the area classified as first-year ice as white. I'm sorry, multi-year ice is white. First year ice is light blue, this little cyan color. Here's a time series from 2003 to 2009, which we've now extended to 2016. Notice what happens to multi-year ice. It's being advected, that is moved, from the from the Arctic Ocean down into the northern Atlantic where it melts. And in fact, in 2008, there was no multi-year ice at the North Pole. So the question is the Arctic ice cap melting? And the short answer is yes. It dropped by more than half in just that amount of time. Now, the winter time series coverage is about the same. This is midwinter, okay? So here's that histogram. See, it's a time series over a decade here. And this is the area of the ice cover, okay? We noticed that the summer melt, the minimum area, is a trend, reducing with a function of time. But the winter, the maximum ice extent, has remained roughly constant. This is actually one of the predictions of climate sciences. As the climate as the climate warms, you'll see more melting of summer ice, and but the winter ice won't really change. But we get to the point that during the summer, there is no multi-year ice. Unfortunately, multi-year ice is really important in insulating the Arctic Ocean from cold winter weather because it's much thicker than the first year ice. And so this affects the bottom water production, therefore the thermal haline solution that keeps the Earth's climate warm. Okay. We can use the scatterometer data to measure backscatter and anisotropy over the Antarctica, which allows us to measure wind direction by looking at the sort of the thing over Antarctica. We can do that over sand dunes as well. We've done that as well. I was going to talk about rain, but in the interest of time, I'm going to skip that. And I just want to talk very briefly, a couple of minutes, just a few minutes, about synthetic aperture radar. This is a synthetic aperture radar image of Saudi Arabia. This is the sand dunes in Saudi Arabia. This brown areas called the empty quarter, where basically hardly anybody goes. These are the mountains that lead down into Oman. In ancient times, peoples would harvest pine tree sap, frankincense, and they'd be hauled to a city, the city of Ubar, which collapsed, was lost to the Western world for 1,000 years until it was found by looking at these trails that they saw. These trails were created by camels and other animals who would trudge across the desert, and they would end up sorting the rocks. And you're looking at the backscatter differences at different frequencies between one kind of rock and another kind of dust and rock. And they all led here. People went there and found the remains of a city of Umar. Here is an example of sand penetration. This is a Landsat image, an optical image of southern Egypt. This is a SAR image taken at the same time, laid on top. There's not much detail, it's just sand. But the SAR image, the microwave data, penetrated, and you can see the remains of riverbed. It's been suggested that a river system as large as that of the Amazon once drained the Sahara Desert, and that perhaps as recently as 50,000 years ago, this was still active as a drainage system, which has profound implications for human development and civilization and things. Here's a SAR image of my campus. I actually live in this building right up here, where all of our administrators live right there, and I like to show a picture of our stadium. BYU's got a good football team, does pretty well sometimes. Typically loses the dumb teams and beats really good teams. But anyway, that's another story. What can you see in that? Well, that's a lot of man-made things. So let's look at what we can see in other things. Here is a synthetic aperture radar image made of some aircraft. It shows both the strength and weakness of the imaging process. In the parking lot here, these are cars. The bright spots are glare, where you're getting corner reflector effects from the various parts of the cars, truck beds, things like that. But this is a nice one. This picture was taken at Ka band, which is a little higher frequency, about 24 gigahertz. It was taken with the radar above it. And looking down, you can see that the wings of the aircraft don't have much backscatter. But because they're closer than the ground, the wings appear shifted toward the radar. And here is the shadow of the radar wings on the ground. Well, this works for buildings just as well as it works for things. And we can do other stuff with it. I want to show you one last slide, and that's this one. Here is a landslide that we observed with the synthetic aperture radar that we built at BYU, one of the first ones we built. This is the Slumgullion landslide in Colorado. It's a bunch of land that flowed down here and dammed off a lake, a river that created a huge lake. And this is the radar image showing the stress lines down there. And we use synthetic aperture radar techniques to create a 3D dimensional image of this thing. And my system isn't working to show this in 3D, but it illustrates what you can do with this kind of thing. Similar, here's a 3-dimensional image produced from synthetic aperture radar system. Okay, well, that's what I have. I cut the time a little close, I apologize, but I wanted to give you a really good dose of microwave remote sensing. Thank you.
That was fantastic. I love all the examples. We're at 4:30, but I definitely don't want to depart without those that do have to leave at 4:30. We get it, but please, if you have any questions, I'm sure there's probably a few questions out there. Now would be a good time to ask.
This is called Stump the Professor. My students play it every day.
So in the first thing you were showing us, the satellite or the dish is actually rotating?
Yes, this is was a pencil beam scatterometer system, and it did a rotating thing. So here is the slide here. I'll share my screen real quick for a second here. Oops, I want to hang on just a second. Yeah, I'm just going to share the actual presentation. I can flip around it easier. But that dish rotates. You can see it kind of rotating this animation here. It points in different directions, so it sweeps out a wide swath.
So something like a phased radar array, you'd need maybe something bigger, or?
Yes. So for synthetic aperture radar, for example, like TerraSAR-X, which is a big satellite that the Europeans operate, the antenna has to be quite large. Their antenna is 10 meters long,
Okay.
and I think it's half a meter wide, if I remember correctly. It's a very large antenna. It has a very narrow swath. Its swath is only the size of one of the footprints of this spacecraft. This spacecraft produces a swath that's 1,800 kilometers wide by doing this rotating beam, whereas the swath width of the TerraSAR-X, when they want to do their high resolution images, is only like 10 to 15 kilometers. And if they do some experimental stuff, they get up to 500. But that's the best you can do with the SAR from space.
Well, thank you very much for the talk. It was excellent.
The other thing you might want to appreciate about this is the transmitter on this particular system is 100 watts. The synthetic aperture radar used on TerraSAR-X is 5 kilowatts.
Yeah.
Yeah. Any other questions?
Hi, this is Tony. Nice talk. Can you say anything about any codes that might be used to help you understand somebody understands scattering from different types of materials and sizes of materials and so on? Are there specific codes you're interested in?
So this is what I'm going to refer you to. Shamelessly, I'm going to promote my book. Okay, this is a book that we put in that's sort of a textbook on microwave remote sensing. And the reason I pull it up right there is we've included a bunch of code, MATLAB codes that you can download. They're even available on the IEEE GRS remote sensing code library that give scattering and radiometric emission models. You can plug in parameters and it'll give you, for at least some well-known surfaces, the scattering cross-sections. Dr. Ullaby, Professor Ullaby, is also working on a generalized database so you can plug in almost anything, and it'll look through its database of previous measurements and other models to give you an estimate of the backscatter for that type of material. One of the difficulties, in remote sensing is that the amount of information required to model any object well is enormous, and especially if you have details of leaf sizes and distributions and stuff. And so we end up doing some sort of approximations or bulk model. And so the models are only as good as the assumptions we put into them.
Excellent. Thanks, Tony. Any other questions? I guess I have a general question. So a lot of this data you showed was from QuickSat.
QuickSat, yeah, QuickSat.
Yeah, and see, I
For
think
quick
you said,
Scatterometer, yeah.
yeah, and you said it was retired somewhere about a couple years ago, 2018-ish. Is that about right? So what's the, I guess a couple questions. What's the game plan moving forward? What's kind of lacking? Where does this go?
So as I showed kind of in the earlier picture, I kind of showed the historical stuff. A lot of other nations have begun orbiting scatterometers, and for reasons that I can't fathom, the US has decided not to fly additional scatterometers. NOAA thought they were too expensive because NASA developed them and flew several, but it was NOAA's turn to pick it up as a standard instrument. But they put all their eggs in radiometer baskets as part of the NPP program, which has not been particularly successful, and we haven't been flying them. So we've been relying a lot on the European ASCAT scatterometer, the Indian OSCAT scatterometer, and recently the Chinese, well, not recently, but they've been flying the HY2A. The US government won't allow us to collaborate with them on this. That's a sort of a problem on that, but they've done quite a bit of work on that. The OSCAT and HY2A, as you can see, are more or less clones of the QuickSat design, the Seawinds design that we developed. We flew Seawinds 3 times. Once on QuickSat, that mission lasted a long time. Once on Audios 2, which only lasted less than a year when the spacecraft failed. And then we flew for 2 years on the International Space Station with RapidScat. Moving forward, I've made several proposals to NASA over the years to fly another scatterometer, and we have additional proposals in process.
Fingers crossed.
Yeah.
Great. Okay, I'll allow another, say 5 seconds or so if anyone else has another question they would like to ask.
I'm not in any big hurry because you're keeping me away from a faculty meeting, which I consider to be a good thing.
I just had one more question. So I was wondering, you mentioned that when you're looking at Antarctic sea ice, you are not able to determine any sort of temperature change based on that because of the number of icebergs. Why can't you take a look at the surface area as well, similar to how you looked at in the Arctic?
So I want to differentiate between icebergs and sea ice. So icebergs, our initial study sort of had a negative result. It wasn't evidence, it was just sort of neutral. The sea ice, interestingly enough, has actually grown. We've done the same study that we did for the Arctic, for the Antarctic. It's actually grown a little bit. We kind of wondered about that. So we go back and talk to the climate modelers, and they say, oh, that's not too surprising. Antarctic ice is always, well, with a few exceptions, is first-year ice. So it grows out to whatever, but then shrinks rapidly back. So we looked at how fast it shrunk back, and we decided that that's actually happening. It's shrinking back faster, but the actual winter extent is about the same. Does that make sense?
Yes, it
One
does.
of the reasons we did the iceberg database is we want to track each iceberg back to its source so that we can determine, is that particular glacier putting out icebergs more often than it used to? Okay. And in some cases, that's been true. The Amery ice shelf has been doing them a lot. And of course, the Lambert ice shelf is actually disintegrated, no longer exists. So it's been doing that.
Okay, thank you.
You're welcome to email me if you want me to follow up on that. I feel like I didn't adequately answer your question.
Yeah, I see we still have 21 participants, attendees. I'll put that out there again. Any other questions? Okay, I think it's towards the end of the day here, so I think people are looking to
people dinner. Don't
wind down a little bit. Yeah, well, I thought it was a fantastic talk. I learned a bunch myself, and I'm glad we were able to connect and you were able to give this presentation as part of our seminar series and GRSS. So
thank you for inviting me.
Yeah. So I hope that our group will chat with you and engage in the future. I know that we have some ongoing meetings with you outside of this with some of the faculty. So hopefully that'll promote some dialogue. And I think with that, that'll conclude our seminar this week. And hopefully we'll be in touch. Thank you, everybody.
Thanks, Dr. Long. Have a good day.
Thank you all.
Thanks. That was really interesting.
Thanks, Emmett. We'll see you later.
Absolutely. Okay, take care.